Hey, we're good to go.
Okay, let me share my screen and hopefully you can see the slide transitions and everything works. Okay, thank you very much for showing up. I do realize it's the end of the semester and we'd all like a much deserved break. So unfortunately, Majid is traveling for conferences. So he's currently in Japan and so he wasn't able to make it. But hopefully today's talk is going to be a brief discussion of the things we do in our lab, as well as things we are looking at for the future. So I'm Vishnu. I work with Professor Majid Zamani, and I'm also working with the PLV lab. And the title for the talk today is Verification of Dynamical Systems via Induction. So I'm briefly going to talk about some of the existing approaches people adopt to try to tackle some interesting problems. So before I get started, the broad outline of the talk is three main sections. The first is what we do. The second, I'm going to take a little bit of a dive into a particular problem, that of ensuring the safety of certain systems, and discuss some of the techniques we've looked at, as well as some possible future directions we're looking at. And finally, I'm going to end with the members in the lab and the different things we're looking at and what we're looking and what we do in general, right? Okay, so with that, we can get started. So first, Professor Majid Zamani is associate professor in the department and also co-associate chair for graduate education, I think. He has one postdoctoral researcher and 5 PhD students. One of those PhD students is me. And he's had many other PhD students and alumni who've gone on to do other things. Some of his master's and PhD students who have graduated have gone on to be postdocs or PhD students in places like California, Berkeley, Max Planck Institute, ETH Zurich, KTH, and places like that. He's had students who've also since gone into academia as faculty, tenure track, in places like Newcastle or the Indian Institute of Science. And of course, it's not just academia. Many of the PhD students have also opted to go into industry. So particularly more in the autonomous systems like Argo AI, autonomous supply, Cariad, and the self-driving cars sort of or autonomous systems things there. And also some master students have gone into places like Qualcomm and Apple. So so there's roughly even split in the students and the alumni in between industry and academia. And usually Majid is more than happy to help in either direction based on what you prefer. So yeah, there are of course positions available if you would like to do your independent study or maybe even pursue a PhD with Majid. There are quite a few articles about him getting a lot of grant money to reason about cyber-physical systems and research and provide guarantees. And that's kind of the main goal of our lab. So basically, we see nowadays that there are growing uses of computational devices in making decisions for a lot of these physical systems. Examples include thermostats, self-driving cars, power grids, pacemakers, and other safety critical devices, as we say. So if in the context of, for example, a self-driving car, while we have an algorithm to decide what speed it should move at and things like that, we would like to ensure that these systems do in fact respect the properties some properties we would like to satisfy. In particular, we would like to ensure that these systems are correct. That is, whatever systems or whatever control design we decide for these systems, we want to ensure that they work, that we have a formal guarantee or some proof or some confidence, in fact, that they work. Any failure in any of these systems could lead to disastrous consequences. If your artificial pacemaker stops working, it could easily lead to loss of life. So the main focus of our lab is all these devices which have these interacting physical and computational elements. How do we reason about such systems, and how do we give guarantees that such systems do work as intended? And so to quote Dijkstra, this is quite a hopefully well-known quote, is we could try to test such systems. But the problem is we can test systems to try to show that there are issues with such systems. But testing alone is not enough to show that there are no issues present in your system. Because you can't exhaustively cover everything. It's either going to be too expensive or not feasible. So really what we would like to, or the focus of our research is at the intersection of control theory and formal methods. Could we provide rigorous mathematical guarantees for our systems? And if so, how do we do that? So that's the main theme of our lab. So certainly there are researchers in CU Boulder who do only one of either control theory or formal methods. We much more prefer to be at the intersection of both. And we would like to reason about all these control systems, but still give formal guarantees of correctness, that they are in fact, as we designed them to be, that they satisfy properties we care about, right? So with that hopefully brief overview, I can dive into one such important property we would like our systems to satisfy. Before that, I'd like to say that the way we're able to model such systems is that, be it pacemakers or be it these autonomous vehicles or thermostats, we have a very nice closed form way of representing such system evolutions based on recurrence relation. Sorry, there is a question in chat. Are there considerations for cases in which rules have to contradict each other? Example, do not exceed n, yeah, do not allow an accident. If the only way to, yeah, so this is a very good question, right? So in particular, if I can formalize your question this way, imagine I give you a set of objectives I want to satisfy, but it's okay for me, but I also give you an ordering on them. And I say, I want to satisfy one objective, even if it costs me not satisfying the other objective at all. So it's known as a lexicographic ordering. So we are definitely looking into notions of what's the right way we want to think about trade-offs and reason about those sort of things. So that's a very good question. Hopefully I have answered that. But yeah, if not, let me know, right? So it's a good question. Yeah, okay. So the nice framework, or the framework I'm going to employ, at least in this talk, is one of a discrete time dynamical system to represent such systems. So let's get into some of the more technical details, hopefully, and then we can broadly pull back and discuss other things we are looking at, right? In particular, I think of my dynamical system to consist of some set of states, which I denote X. So my system can evolve in this region, starting from some initial set of states I. So the system basically evolves by starting from some state, x0, and then according to my transition function f, it's going to move to the next state, x1, and then I apply f and it's going to move to the next state, and this process repeats. So if you think of it, for example, like a thermostat, you don't see my thermostat, when I set my thermostat temperature, let's say to 28 Celsius. I do apologize, I haven't got the conversion to Fahrenheit quite yet. But let's say I do set it to 28 Celsius and the outside ambient temperature is around 10 Celsius. It's not a point where I immediately jump temperatures from one to the other. It's more that it evolves over time, right? And so this is how we kind of think about it, where we start with some initial state and then we keep applying some transition map over and over. And one of the key problems we'd like to ensure is that starting from some initial set of states, we aren't able to get to some bad or unsafe set of states. I do apologize. Was there a question? Yeah, okay. If there's no question, I guess I shall carry on, right? So this is like the first example. So you can think of it like, I don't want my temperature to exceed 33 Celsius, or I don't want my vehicle to leave the lane of the road. I don't want my blood, I don't want the insulin levels to spike too high or too low, those sort of questions, right? So that's so questions of safety. We don't want our systems as they evolve to get into these regions. So the first question is, how do we reason about, or how do we give guarantees that such facts are true about our system? So let's say I design a controller, and maybe my controller works, maybe it doesn't, but it's in this nice closed form expression of it. And I ask you, okay, given this controller, given these initial set of states, can you give me a guarantee that the system does not reach some unsafe or bad regions? Right? So that's the canonical problem of verifying the safety of a system. So I should know that if our system is going to be a finite graph, like in this figure, but I want to say that starting from x0, I don't reach xu. Well, the way we would like to tackle the problem is by using ST reachability. So starting from x0, can I reach this region in my graph? And if so, the problem is solved, and we could say, okay, well, our work's done, we go home, is the hope we have. And in fact, this has a very nice complexity. It's quite easy to do, not too expensive on graphs which are quite large as well. But the problem is, what if our graph have infinitely many vertices? Usually when we try to reason about all these physical components, it's no longer discrete, but we like to reason about values which take continuous values or uncountably many values. So if I'm reasoning about temperature values, it's not a point that the temperature at a given point is just going to be at a particular temperature or it jumps to the next degree Celsius or degree Fahrenheit. It's more that there's a range of values it can take. And these values can take real values. And so the problem is our graphs, when we try to reason about them or when we try to represent them as these dynamical systems, no longer have finitely many vertices, we have infinitely many vertices. So let's try to look at the problem from a high level again. And let's try to say, I give you the sequence, right? So I start from 1, I divide it by 2, I get to a half. I divide it by 2, I get to a fourth. And then I keep repeating the process. And then I say that the state 0.75 is unsafe. So right now, this is me abstracting the problem to a very high level. So this isn't me giving you an actual physical system, but this is just me saying, imagine my system looked like this. How do I try to show that starting from 1, I don't reach 0.75? Certainly, this is a true fact, you could say. And you could say, you can make that observation. But how do we rigorously prove it? And ideally, what we'd like to build up is we'd like to build up an idea where we can prove it by not using a handwritten proof, but rather asking our computers to do the hard work for us and asking it to prove it for us instead of us having to prove it, right? So let's try to think of this, and I'll frame this now as a dynamical system, right? So consider my set of states to be in between 0 and 2, my initial set of states denoted I to be in between 0.9 and 1.1. And my system evolves by taking the current state, dividing the current state by 2, and moving to that state. So if I'm in state 1, I divide it by 2, I go to state 0.5, divide by 2, I get to 0.25, and the process repeats. The same for 1.1, the same for 0.9, and you can observe that there are infinitely many values which I haven't drawn, but the same idea follows. And so I ask the question, okay, for this system, is the state 0.75 reachable? So hopefully we are okay with the problem setup. And if you feel there are any issues, do let me know, or do chime in chat, or if something's unclear, I'm happy to hopefully clarify it, right? Okay, well, I don't see any questions in chat. So hopefully we're all on the same page, but do interrupt me if there are any issues. So the way we would like to tackle this, or the way we would like to think about this is, could we use induction to reason about this? Could we prove such a property inductively? First, so to do that, let's try to see how we'd like to think about this inductively. So consider my same system and observe that I can think of all the states my system reaches from my initial state in somewhat of an inductive fashion. I say that a state of my system is reachable if it's an initial state, because this is vacuously true. If I can start from somewhere, that better be reachable. The second thing I can think of is, suppose I do reach some state. I don't know what the state is, but let's just say I reach some state X. Then if the state X is reachable, then me applying F to X should lead me to a state that is still reachable. And this is kind of what we would like to try to form inductive proofs on and try to give those sort of guarantees. So let's try to think about this in this recursive fashion, right? So as I said, we consider any initial state to be reachable because you can start from there. So you're, of course, by definition reachable. And I say that I denote it by the set reach. Or alternatively, if I am starting from some state X, which is reachable, then applying my function map f should still keep me reachable. And so if I can show a property, or the way I would like to use structural induction is if I want to show a property P to be true about all the states that are reachable by my system, well, I just need to show that such a property is true in my initial set of states. And if the property was to be true in some state, then applying my transition function or my map f should still preserve the truth of property P, right? So this is kind of the high level way we'd like to go around trying to prove it. So I take my same example again, which is just keep dividing by 2 over and over. Observe that at some point I will reach 0, and once I reach 0, I will loop on 0. And then I try to ask, okay, what's a good property I can try to show of everything that's reachable, which excludes 0.75? So what properties should I try to consider? Well, why not we go with the property that whatever state is reachable is not 0.75, right? This seems like the simplest property, which I would like to show, which will still guarantee that my system doesn't reach 0.75. So to do that, I have to, and I want to show that this is a property which holds true inductively on my system. So to do that, I could show it for the base case, which is I show it for everything which is the initial set of states. So observe that everything between 0.9 and 1.1 is strictly bigger than 0.75, and none of them are equal to 0.75. So this trivially satisfies it. Now the question is, while this may satisfy it, is this something that holds inductively? So is there some state x such that if I apply f to that state, I'm able to get to 0.75, and that state x is not 0.75. So hopefully I'll stop here and ask a question to the audience to either give me a witness that it fails or some idea of why it wouldn't fail, right? So hopefully we are on roughly the same page. Anyone in the audience would like to try to venture a guess? Well, let me, yes, exactly. Thank you. Yeah, precisely. So if I consider the state to be 1.5, unfortunately, if I consider x to be 1.5, certainly 1.5 is not 0.75, and so the property holds. But then when I divide 1.5 by 2, I get to 0.75, and the property doesn't hold, right? So exactly. So unfortunately, while my property I chose was x is not equal to 0.75, I wasn't able to inductively show this property to be true. Though this property is true, it's not it's not something I can inductively show. So I would like to think of a different property. And so I think of a modification to the property, and instead of saying, oh, it's not 0.75 because it's not inductive, let's say it's not 0.75, and I also say x must be between 0 and 1.1. So if I do consider x to be this to be my property, is such a property inductive? So I'm not going to spend hopefully too much time, but observe that the initial set of states do satisfy this condition. Furthermore, let's show this inductively. Assume some state x satisfies this. Then if a state x satisfies it, I need to show that f of x also satisfies it. Well, if x satisfies this, then I know f of x is x over 2. So if x satisfies this, then f of x is in between 0 and 0.55. And if f of x is between the two, then 0 is, then I can show it's in between 0 and 1.1 as well. And therefore, I can show that if x satisfies above, then so does f of x. And this fact is enough to show that this new property is inductive. But the problem, so this is inductive, and it's enough to show that the system starting from the initial set of states doesn't reach an unsafe state. But I did have to go through the effort of telling you what this property is, making changes to this property, and trying this again. So the point is, I had to know something about the system. I had to manually reason about the system as well as the function f to try to find a proof. So the question is, is there a way I can try to generalize this proof? And instead of me manually making this effort, is there a way I can automate the search for a property which is inductive and show that in a way where my computer runs code? And then if I'm successful, then I don't really need to put in the effort. I can say, because my code runs and it gives me a result, that acts as a proof that the system is safe. And this is one of the key ideas we kind of build on in all of our research in different contexts, right? So the idea is, imagine I could show a property to be true on my reachable states and then show its negation is true on the unsafe states. Then, in particular, the property we consider are inequalities with respect to a function. So this has been well-established literature, well-established research, which we've kind of been building on. And this has been the notion of barrier certificates. And the idea of a barrier certificate is, suppose this was introduced by Prasna and Jadbhai back in 2004, I think, or 5. And the idea of a barrier certificate is it's going to be a function from my states to real values, and then it has to satisfy some conditions. So hopefully this figure is illustrative, but I'll go through the figure in a bit, right? So I'm going to use this to denote all the states of my system. And the first condition I have is that the value of the barrier is less than or equal to 0 in all my initial states. So imagine this figure here inside mine, this polygon, to represent all those points which have a value which are less than or equal to 0. Then this polygon inside it to have values which are less than or equal to some negative value, and so on as I keep going inside, right? So basically, the first condition I want to show is that such a function should always be bounded by some, I choose 0 for this case, for illustration. And furthermore, suppose that me applying the function f to my system keeps me inside this region. That is, I have this non-increased value as I apply my function f. So imagine I start from some point here, and then I apply f. I have to remain within this 0 set. Then any initial state or any system starting from the initial set of states is constrained to remain within the 0 set. And so all I need to show is that in my unsafe region, this value is going to be bigger than 0, and these two sets don't overlap. And if I can show that, then I'm able to show that my system is indeed safe. And this kind of approach has been popularized. Sorry, I seem to have a question in chat. That f of x is a black box. Yeah, a very good question. So that's a very good question. I will get back to f of x being a black box in our research slide at the end. But thank you for that question. Right now, I'm going to assume you know function f. I'm going to assume you know function f. And then you can try to find such functions b by relying on optimization techniques. So I'm not going to into too much details about those, but hopefully if you're interested, there are very nice convex optimization courses as well as linear programming courses offered by the department. So that's the broad, that's one of the ideas we're looking at, right? And building off of that. So that's kind of my deep dive. So I'm going to switch gears for the last part of the talk to briefly talk about how we've looked at these approaches and considered different problems and what we are looking at. So the first, instead of using our inductive approaches, there are people who were part of the lab who looked at approaches which don't really rely on these inductive arguments, but rather to think of finite state representations. So this is a paper this is a tool, Scots, which Majid has developed with Matthias Runger back when he was working with him. This has since been improved upon and implemented in CU Boulder by Mohammed Khaled. So we have this lab where we try to show that this particular car is able to avoid the regions in red while reaching the region in green, starting from an initial region. So we synthesize a control policy on the fly, and our control policy is formally correct. We have a mathematical proof that whatever control it designs is correct, assuming it's able to successfully design the controller, right? So that's one aspect we've been looking at. These are the current members of the lab. So that's from top to bottom. This is Bingjo, Asad, me, Daniel, Alireza, and Felipe. And I'll briefly go over the different things we've been looking at. So Felipe and Asad have been looking at large-scale interconnected systems. How do you use such sort of approaches and scale them to systems which are very high dimensions, by trying to break them down and reason about them in a compositional way? uh, Wingshaw, Daniel, Alireza have been looking at data-driven approaches. How do you reason about such systems when you don't know the function f, but still want to give formal guarantees? We've looked at how do you try to give probabilistically approximately correct guarantees. We've looked at how do you give guarantees under some mild assumptions and other things. I'm happy to talk more about it offline. Bingshaw has been looking at how to use sandbox controllers. So if you have an unverified controller implemented as a neural network, how do you build a sandbox environment where you allow the neural network to act so long as it maintains the property of interest? But if the neural network may have a chance of failing, then you want to correct it. So he's been looking at that. Um, Alireza, Felipe, and I have been looking at more complex objectives beyond safety specified by different kinds of automata and how do you reason about them. And finally, Alireza has been looking at how do you use transfer learning as well as neural network representations to learn how do you verify those and transfer guarantees for new systems, right? So this is all of us in the lab. Our lab web page is there. And I will end my talk, I guess. There, I do have a little bit of transition where I wanted to show you this example in code, but I will defer that to after the question and answers, I guess, because if you're not interested, you can choose to avoid that, right? But I'll take the same example we had and I have some code which runs it on that and checks it. So with that, thank you. That's my talk, and I will take questions now before switching back to hopefully talk about some of the implementation, right? Okay.
Thank you, Vishnu. Please feel free to unmute yourself and ask questions or post in chat. We have a pretty small group, so you can unmute yourself and ask as well.
So I guess thank you for the talk, Vishnu. It was really fun. I'm really interested in knowing a little bit more about the probabilistic approaches, right? Especially in highly dynamic, highly scaled systems. It may be more valuable to use some kind of combination of probabilities and sandboxing, right?
Absolutely right. So I suppose I'd like to tackle this question in two directions. The first is when I don't know my function f or how my system exactly evolves, like I don't have a good representation of it. In that case, when I sample maybe some set of points, and then I try to build those guarantees from my sample points. And the second way I want to look at it is instead of me trying to look at my system, my function f as unknown, I think of it as it's known, but I have some stochastic nature to it. So that's another way I can think of it, right? So both of these approaches we've looked at in different ways. For the first approaches, we've looked at ways of trying to give probabilistic guarantees with some confidence. And for the second, you still get probabilistic guarantees. It's just the way we try to give these probabilistic guarantees turn out to be different. So in the first setting, when we try to do it, we try to assume some sort of continuity in our system. And that kind of gives us some added benefit of if we sample enough points, then we get some quite a high confidence that it should be true, assuming some nice continuity. In the other direction, if you want to try to give probabilistic guarantees, the way you want to think of this process evolution is you'd like to try to, instead of my inequality there, you want that inequality with respect to an expectation. So you want to think of the process to be some sort of like a martingale or super martingale process. And that kind of gives you a nice probabilistic guarantees here. Of course, how we extend those for more complex properties is a very good question and something we're actively working on.
Yeah, I'm thinking like of real world autonomous systems where maybe you have a series of models you're using at different levels of some are more open and some are more conservative, and you're just like looking for some kind of safety metric and switching between the models based on where the models suggest in a particular safety within that particular safety metric. Is that kind of some approaches?
Um,
And then of course you can sample that back,
yeah.
right, in kind of a Bayesian kind of way, and use that to refine the metrics.
Yeah, so I suppose I'd say we haven't exactly looked at it in that context, but I think I do understand your meaning in that I try to say that I have different ways or different coarseness to representing my system in different contexts. So I care more about this particular detail with this degree of coarseness. And I care about it here and I try to verify something, but my system may be in any of those. And then how do you kind of verify that, right? So this is kind of like not exactly similar, but the way you may think of it in different ways, imagine I could switch between these different levels of coarseness. And then I try to say, okay, if I can switch between these different levels of coarseness, then for a particular degree of coarseness, how much can you give me a guarantee of satisfying this? So that's something we've kind of looked at a little bit, yeah. But it's slightly different.
Yeah, I think that a lot of the real world problems, one model doesn't fit everything, right? So you have to decide, maybe there's a model of models where you decide which model you're going to use, that kind of thing.
Yeah, no, that's why Majid has been really pushing for data-driven approaches recently, where he's like, oh, assume you don't know anything about your system model, but you get data. You're allowed like a black box.
In your example, right, it was really easy to inverse the function.
Yes.
But in most real world examples, you can't inverse it.
Yeah, absolutely. Right. And the conditions also, which I did say at the end, didn't really care about you inverting them, right? So they didn't ask for an inverse. They asked you to find a new function such that its composition gives you those guarantees. And that's kind of what we've been using for data-driven approaches, where you try to say, if I sample enough points and I'm able to observe the evolution, then I can give you some confidence that, or I can give you this threshold of confidence, like 10 to the power minus 5 or whatever.
So then, yeah, you're looking at it from a statistical approach then.
Yeah, exactly.
And then there comes in the question of, in a verification system, what level of squishiness is there allowed? Like, what's your p-value that are okay?
Yeah, absolutely.
Yeah, and I guess that's less of a research problem as it is a business problem, right? Because tight p-values mean it's harder to calculate things, but
yeah, you try for the best you can get, and hopefully that's good enough that you're comfortable with that. Or if you want tighter guarantees, then we need more assumptions and more data. So that's kind of how it is. So we do have guarantees where we can just use data without any confidence. We can give a 100% guarantee, but those require more data and more of a, yeah, you need Lipschitz continuity and you need to use a bit of triangle inequality to bound some things. So there's a little bit you need to know about your system. Like you need to know function f is Lipschitz continuous with this constant, and then you can kind of give some guarantees, right? So,
right. I don't want to monopolize the time. I'll go ahead and let anyone else take the floor. Thank you very much.
yeah. Okay, well, if there are no questions, I'll briefly just say that for my example, which I showed, maybe I won't show you the code, but here's how the function looks. So for the example, I basically ran a program to search for a function. This is the function I got. And you can kind of see that in between 0.9 to 1.1, it's less than 0. And at 0.75, I need to really magnify this. But you can see it's just about bigger than 0. So it kind of gives you that sort of guarantee with this function, which satisfies those sort of conditions, right? So yeah, you can play around and it's quite nice, but I guess that's, yeah.
Okay, thank you so much, Vishnu, for your time today. And I hope it was helpful for people looking for PhDs. I know Majid is looking for PhD students.
Majid is happy to take PhD students for independent research, but as long as
Yep, definitely.
as long as you feel this is interesting and you'd like to look at things at the intersection of control theory and form methods, we're more than happy to talk.
Vishnu, would you mind, if you're okay, adding your email address if
Oh
people have?
yes, absolutely. I apologize. Let me just add that in chat, right? So this is my, I don't think capitalization matters.
Yeah.
But hopefully it's fine. Yeah. Okay.
Thank you so much, everybody.
Thank you. Have a good week.
Too.